Hello everyone, it's Benny, and in this video we're going to be making our monster actually attack the player. Well, sort of. We're going to be able to detect if his bullet actually hits the player, and we're going to be able to make him, sort of cast the bullet out into the world and see where it hits. And that'll be sort of the first step, and we'll sort of go from there and see how advanced we can make our monster actually behave when shooting our player. And yeah. So, first off, we're going to need to use the attack state, so I'm going to make our monster start in the attack state. And after the attack state's done, I'm just going to make him go back to the chase state, just so we don't end up attacking infinitely. Just one attack should be enough anyways. Now, you may be thinking that, okay, if we're going to make the enemy shoot the player, we're going to cast out some ray from the monster towards the player, and from there, what we're going to do is we're going to see where that intersects, and we're going to calculate the intersection point, and do all that fancy nonsense. And, in most cases, you'd be right. But the problem is, that would actually make sense. You see, we don't have a physics engine. We can't do a lot of things that make sense very easily. So instead, we're going to be doing a ridiculous line intersection nonsense. So, that's how it's going to work. We're going to create a line going from our monster to our player. Well, in the direction of our player, it's going to go off to some finite distance. And we're going to see what parts of the world that intersects. And if one of them is a player, and if it is the player, then, well, we're going to be able to determine that we hit the player and, all that stuff. That, of course, all starts with just a vector 2f called line start, which is just going to be where we are. That's where everything starts. But unfortunately, we don't have any swizzling, so we're going to have to construct this manually. .get x, transform, .get translation, .get z. All on the xz plane. Now we also are going to need a vector 2f called sort of cast direction, which is going to be sort of the same thing except for orientation. The good thing is our orientation is in the direction of our player, so we don't need to do anything very complex to figure out which direction the player's in. Well, technically it's towards the camera, but because I'm not doing any cinematic stuff, I can safely assume that the camera will be the player. Definitely not the best coding practice, but hey. And finally, we're going to need some vector 2f line end for where this line actually ends. And that's not going to need any fancy stuff, actually. It's just going to be line start plus the cast direction times, I don't know, shoot distance. How far we can shoot, and that'll be a constant. So, I can create constant, which is going to be the shoot distance, and I'll just set that to 1,000. It really doesn't matter as long as it's something much bigger than your level, so, yeah. And with that, what we're going to do is we're going to need to figure out if we collide, so we can have some collision vector spelled correctly. And we don't have a method for this yet, but I'll go ahead and write it out anyways. This is going to be equal to check intersections for the line start and the line end. We can have some method for that. And if this vector is null, then we didn't hit anything. That should never, ever, ever happen, so that means our code's gone horribly wrong, but just in case, println, we've missed everything. Quite impressive, but oh well, we somehow managed to do it. Otherwise, we're going to say we hit something. And this is sort of the framework we're going to be going for in this video. So, we hit something. Yeah, this is sort of the framework we're going to be going for in this video. We're going to try to make it so that we can accurately determine that we hit something. And that all starts with needing to figure out all intersections. So let's go to level. Let's go to undercheck collisions. And let's create public vector 2f check intersections, taking in vector 2f line start and line end. Now what this method's going to do is it's going to find the nearest intersection to the start of the line that we're putting in. So we're going to have some vector 2f nearest intersection, which is going to start off equal to null. We're not guaranteed technically to hit anything, although we should unless we have a really poorly designed level. And I'm just going to return that right now. Return the nearest intersection. And right now if I run, it should just keep telling us that we missed. Or just tell us once and then keep going. Yep, we've missed everything. That's okay, because now we're going to need to actually detect intersections. And unfortunately, that's going to require us to, well, we're going to need to convert our level into all the different lines that we can intersect with. And that's really not best done every time we need to check intersections, so I'm going to do that as part of the level generation. I'm going to have some array lists of vector 2f, collision pass start, and collision pass end. And these will be just the list of all the different lines that we could possibly collide with that represents our level. And we're going to generate this sort of virtual collision mesh in our generate level method. And you could do some stuff in the actual check collisions method based on the, what's it called? Just the level image, and that would work fine too. I'm just doing it this way because, well, I find this way a little bit easier to do personally, but hey. So here's how we're going to generate the mesh. In our check where we're determining where the walls are, that's exactly what we're going to do. We already have a nice check going on here, determining where the wall is, what the line is like, and from that, it's determining how we can create the actual planes that are showing the image of our level. We're just going to need to do the exact same sort of check, except to generate the lines that bound our level. Now, I've already set up a bit of an image here that's going to help us visualize this. So, our x and y position in the generate level method start right here, ij, at the top corner. Now in here, if this is true, it's j minus 1. And minus an image goes up, so that means there's a wall right here. So how do we detect this? Well, we're going to need to add a couple of vector 2s. We're going to add to the start, well, first of all, we're just going to add something, but what we're going to do is we're going to add something at just the I position times the spot width, got to take into account the size of the level, and j times spot length. Because that's where it starts. It starts at this position, and we also want it at this position. That requires increasing I, so, and that will be the end position, so collision pass end, almost the same thing, except I plus 1. And with that, we now have this line added to our big giant list of all the lines in the level. Now, what we're going to do is we're going to do the same sort of check except for the one below. And that's actually going to end up being mostly the same line, except it's going to be j plus 1 instead. So, that's actually pretty simple. The whole process of generating the mesh is pretty simple, actually. It's just figuring out which wall is correct. Now this one is if there's a wall right here. So that's going to require a starting point at I comma j, so that's the start point. The end point is going to be I comma j plus 1, because if you add 1 to j, that takes you right there. So that gets us that line. And lastly, we have, if we have a wall right here. And similarly, that's going to be pretty much the same thing, except plus 1 on the I-axis, or plus 1 to I. So, with that, congratulations, we've generated our collision mesh. And now all we have to do is iterate through it and figure out where the intersection is. So, we do a for loop, I is less than the start.size, I plus plus. And, yeah. And for every single one, we're going to perform some line intersection check. So, private vector 2f is going to be called line intersect because we don't have a physics thing. It's going to take in line start 1. Yeah, vector 2f line end 1. I'll just type it out. And there. And then, no, it's going to take line start 2 and line end 2. And for now, I'm just going to return null. It's just to have something here that, you know, act as a prototype for what works. And now, what I'm going to do, again, just perform that check. So vector 2f collision vector is going to equal if we intersect from our line start and line end. And by the way, this method is going to return the position we intersect at. So between that and whatever collision path.get I and collision path.end.get I. Whatever line that is. And that will perform the intersection check and return whatnot. And yeah. So if nearest intersection is not equal to null. Wait, these are conditions that, hang on, let's take a step back here. What we're going to do once we have our collision vector is we're going to compare it to our nearest intersection vector, and if our collision vector is closer than our nearest intersection vector, then we're going to replace the nearest intersection vector with whatever our collision vector is. So first off, if our nearest intersection vector is null, then of course we're going to want to assign it. Although actually, I want to say if collision vector is not equal to null, well, you know, no. I always want to assign it if that's null, because it doesn't matter. If the collision vector is also null, then it's just going to replace it next iteration. Doesn't really matter. If that's null, or collision vector is not equal to null, and this is where we're going to actually perform the nearest check. And there's better ways. And there's some better ways to do this, but, well, vaguely better ways, but I'm just going to do it like this because it's easy. Now we want to find the nearest one to line start. So first off, we're going to say nearest intersection minus line start dot length. If this is less than collision vector minus line start dot length, then, yeah, then it's nearer, clearly. And I don't want 10 million tabs, thank you. Whew. So those are our two conditions. Well, technically 3, but we're going to want to assign collision vector to the nearest intersection. Well, in fact, I can go ahead and do that. Nearest intersection equals collision vector. We're going to want to perform this assignment if either there is no nearest intersection yet, or collision vector is not equal to null. Well, yeah. Actually, let's reverse that. If collision vector is not equal to null, and nearest intersection, yeah, either nearest intersection is null, or the nearest intersection is closer than, wait, if it's further away than the collision vector. And this should still do absolutely nothing, because we're always returning null, but at least shouldn't crash. That's what I'm going for here. Good. No crashes yet. Everything's working out fine. Sort of. So all that we've narrowed the problem down to is how do we detect if two lines intersect? And this is where things get a little bit tricky. Now here's sort of the algorithm I'm going to go for. I'm going to say, well, first off, let me do it like this. I'm going to say vector 2f line 1, that's going to equal line end 1 minus line start 1. And line 2, so I'm actually calculating the sort of like line fragments that go from the origin. You know what I'm doing, even if I can't really explain it very well right now, or I just can't think of a good way to explain it. I'm finding the actual sort of vector representation of the line from the end and the start, you know? That. So I've got the line. So now, of course, if I do line start 1 plus line 1, that's going to equal line end 1, just by nature. But here's the thing. What I want to know, how I'm going to solve this is I'm going to say, if there's some value a, where I can add it so that line start 2 plus line 2 times b, some value b, it's just something that makes these equal. If I can find something that makes this equal, then I know that they intersect. That should be the intersection point. That's sort of the algorithm I'm using, if that should make sense, I hope. So yeah, if they do indeed intersect, I should be able to scale down this line mount so that they both equal the intersection point. That's the idea. The only trick is actually finding those, and that can involve some interesting algebra. So here's what I'm going to do. Since it's going to take me too long to explain it here, I am going to explain it in the 3D engine series, but, well, when I do physics there. But if you're interested in explanation right now, here's a question on... Forgot to put comment. This is a question on Stack Overflow, which has some answers that do a pretty good job of explaining the algebra of how you actually calculate A and B. I'm going to be performing the sort of optimized final algebraic step, I guess, but if you want to figure out how to derive it and whatnot, that's a good place to look. I'll be explaining it again in the 3D series when it's appropriate, but yeah. However, in order to do this big calculation, we're going to need a vector function that we don't have. The cross product. Unfortunately, we don't have a cross product for our vector 2's. And cross product would be the sine of the angle between the two vectors we're crossing. So, in order to make this convenient, I'm going to create a vector 2f cross method in here. It takes in vector 2fa and vector 2fb. But I'm going to add a little note, not at the bottom, but right here, which states just vector 2f cross product, because we really shouldn't need to implement our own method for this. Oh, and it returns a float, of course, because, again, the cross product would be equal to the sine of the angle between them. So, of course, that would be a float. Or a double, but I'm doing floats, so yeah. And how you actually calculate this is pretty simple. A.getX times B.getY minus A.getY times B.getX. And I'll probably talk about why that works at some point when I'm talking about vector math. But again, I'm more interested in performing the actual line intersection than all the derivation and nonsense. At least right now. So now, as for actually performing the line intersection, first off, we want to do something a little bit simpler than actually performing the full-on line intersection check. For one, I want to create float cross, which is, well, okay, vector 2f cross between our two lines. And the big reason I want to do this right now is because if cross is equal to 0, I'm going to return null. And here's how this works. If the sine of the angle between these two lines is 0, then they must be parallel. And if they're parallel, then they never intersect, so I have to return null. They can't possibly be intersecting because they're parallel. Now, if they're not parallel, this is where things get a little bit more interesting. For one, I'm going to need a vector that takes... I'll call it this for now, but I'm going to rename it to something more appropriate. I just can't think of a good name right now. What I'm doing is I'm taking the start positions of the two lines, and I'm just subtracting them, creating the line between the start positions. So, I guess, distance between line starts. There. And the reason is because this is going to be vital in calculating these A and B constants that will determine if they intersect, because if they're not parallel, then there will be some A and B that make them align. The only question ultimately will be is do they align within the length of the line, if that makes any sense. And that'll be the more that'll be actually pretty easy, but you'll see. Anyways, the way we calculate this, we're going to take the sine of the angle between the sine of the angle between the distance of the line starts and line 2. That will give us the amount we need to scale line 1. Or after we divide that by the cross product. Wait, vector 2f cross of that. And again, if you want to know the mathematical derivation of this, this is a good place to look. I'm not going to go over it now because it would take me too long to go through the derivation. But yeah, that's the ultimate calculation you need to perform. And B is the same thing except for line 1. And there. So now we have A and B. We have these constant values. The real question at this point is, are they within range? Because if A is like something like 1.5, then technically it's correct, but that will be beyond the length of the line. That will give me something beyond the line end. So I want to say if 0 is less than A, and A is less than 1.0. So if it's on a range between 0 and 1, essentially, then that means it will actually be within range. Because again, if it's negative, that will be before the start of the line, which doesn't make sense. If it's greater than 1, then it's far out beyond the end of the line. And same thing for B. 0.0f is less than B. And wait, I shouldn't be doing less than, I should be... Wait a minute. Let me just write it out, and then I'll worry about this. So, and B is less than 1.0. So, yeah. I want to check if it's within range, so not less than that. So if all this, then so if it's within the range of 0 to 1, both of them, then we do know that indeed there is some value, A, that would scale it, and some value B that scales it. Now, ultimately, you can use either one of these now that you know them. So, for example, I could return line start 1 dot add line 1 times A, and that would be the intersection point. Or I could do the same thing for line 2, or line start 2, line 2, and B. They're equal, so it doesn't matter, but yeah. And that's how you perform line intersection. So at this point, we should have proper intersection if I run. It should say we actually hit something. We've missed everything. Okay. And that ultimately means I've screwed up somewhere in this calculation. So, one moment while I go ahead and debug this. And I just made a couple typos. No big deal. First off, I shouldn't be checking if 0 is greater than A. I want to know if A is greater than 0. So, yeah. This does check if it's in the range of 0 to 1. I don't know why I thought it was the other way around. And yeah. Secondly, if I want to measure the distance between line start 2 and line start 1, I really shouldn't be subtracting line start 2 from itself. So yeah, that should be line start 1 right there. So if I flip those two signs and change that, then it's well, it actually works, I should say. So yeah, now he's actually hitting something, which is exactly what I'm going for. So cool, now we've got things that hit things. Now, as for whether this actually hits the player or not, that can be a little bit more of a challenge. And actually, I think we've done enough in this video. It's gone on for a fair while, and I think there's enough, so thank you. Hope you enjoyed, hope you learned, and next time we're going to figure out not just how to detect if it hits the walls, but whether it hit the player or not. And that'll be our next goal. So thank you. Hope you enjoyed, hope you learned, and see you next time.